Let's have a little look at Surge and Swab now. After completing this module, you'll be able to describe what Surge and Swab actually are, list the primary influences on Surge and Swab, and describe the constraints within which Surge and Swab pressures must be maintained, and also understand what's required to effectively monitor Surge and Swab. There are three effects in the literature which are said to create a surge or swab pressure in the wellbore as the pipe is moved. And these are breaking the gel strength of the mud, inertial effects, which I'll explain in a minute, and viscous drag. Breaking the gel strength of the mud first. Now, as we presented previously under other parts of this course, basically the gel strength of the mud must actually be overcome to initiate flow. And once the gel's broken, that relationship ceases to be relevant. So basically, in Surge and Swab, yes, there may be an effect where you have to break the gels, but when you've actually started tripping in or tripping out, the Surge and Swab pressure's got very little to do with this once the mud's actually sheared and actually moving. Inertial effects, well, that's basically the tendency of mud to resist a change in motion. As you know, that inertia is basically the resistance of a body to change its state. It could be from rest to moving, or from moving at one speed to moving at another. So the inertial effects on mud is basically the tendency of the mud to actually resist changing its state as well. And this can actually be worked out using these sort of equations. Basically, pressure equals the length of the section in which your pipe is, the density of the mud, the acceleration of the pipe, the square of the diameter of the pipe divided by a gravitational constant, and then in brackets here we've got the square of the hole diameter minus the square of the pipe diameter. That's for closed pipe. For open pipe, it's basically, instead of the external diameter of the pipe being squared on the top, you've just got the external minus the internal diameter of the pipe. And again, you've got an internal diameter of the pipe squared on the bottom here as well. So you've got closed and open pipe for inertial effects. The inertial effects are rarely taken into account in Surge and Swab equations or calculations or any of the software that we use. And by far and away, the greatest effect on pressure throughout the annulus during surge, when we're looking at Surge and Swab, is actually what's called viscous drag. And the equations for viscous drag, just to quickly show you what these are, we've got the velocity of the mud clinging to the pipe is basically the velocity of the pipe times some constant, which is called negative K, which is actually the Burckhardt clinging constant. I'll explain that on the next slide, what sort of value that K value actually is. And then there's mud clinging to the borehole wall. Well, basically, what we're saying here is we've got mud clinging to the pipe, mud clinging to the borehole wall, and that's not wanting to move, and we've actually got the pipe going into the wellbore displacing mud up the wellbore as you put pipe in, or the opposite way around. If you're pulling pipe out, mud's entering the wellbore and flowing down to replace the volume of the steel that you're pulling out. Plus, you've also got the motion of the pipe itself, and the fact that mud is wanting to cling to the pipe wall and the borehole wall. So as you move the pipe up, you're effectively pulling some of that mud up with the pipe, or as you're running in, you're pushing some of it in. There's mud clinging to the outside of the pipe, and there's also mud clinging to the borehole, which isn't moving. So we've got two effects, two extremes there. You've got the mud on the pipe, mud on the hole, not wanting to move, and you've also got the velocity of the pipe and the velocity of that fluid. So the mud clinging to the borehole wall is given by this equation. It's minus the square of the pipe diameter divided by the square of the hole diameter minus the square of the pipe diameter times the velocity of the pipe again. So this is the velocity of that mud in the annulus there. And combining these two equations, you get the velocity for an average effective annular, well, it's the average effective annular velocity, VAE, and that's minus d squared for the pipe divided by d squared for the hole minus d squared for the pipe, which is the diameters from here, plus the Burckhardt clinging constant, which comes from here, times the velocity of the pipe. And that gives you your viscous drag induced annular velocity, basically. Now, as I mentioned, I would explain K, the Burckhardt clinging constant. Basically, K is generally quoted as 0.45 in most drilling engineering texts. From the actual workings or some of the experiments that were done to determine K, basically there were a couple of curves, one for turbulent flow on the top here and one for laminar flow on the bottom. And along the bottom here we've got the pipe to hole ratio of pipe diameter. What's the ratio of the pipe diameter to the hole diameter? And that's usually somewhere in the region of 0.4. Well, we've got 0.4 to 1 on the x-axis there, but it's usually in this sort of area here where this blue line's going up. The reason that it's normally about 0.45, I would hazard a guess, is that generally the pipe to hole ratios where surge and swab's important, like when you've got 5-inch pipe and 8.5-inch hole, the ratio between 5-inch pipe and 8.5-inch hole is 0.59. If you put 0.59 on the x-axis here and project upwards, somewhere in between the turbulent and laminar flow here, we end up with 0.45. And most pipe to hole ratios will lie somewhere in this region. We know that it's going to be somewhere between turbulent and laminar flow. And we know it's going to be somewhere in this sort of area, so 0.45 seems like a pretty good rule of thumb value. So I think that's where that comes from in most of the literature. So they basically simplify it and make it easy to use manually on a calculator or on a rig. Basically, when we're working out viscous drag, we substitute the effective annular velocity into the flow modeling equations, the same flow modeling equations that we use for annular pressure drop or pipe pressure drop, like the Herschel-Bulkley model. So for the velocity component or the velocity expression in that equation now is the effective annular velocity is substituted for the annular velocity that we would have when we're just pumping mud around. So the effective annular velocity was worked out using that equation on the previous slide. This equation here, effective annular velocity, is your diameter and your clinging constant times the velocity of the velocity of the pipe. So that's put into the Herschel-Bulkley equation, and we can then work out the pressure loss due to fluid flowing past the pipe as normal. So just to show you that kind of thing graphically, I mean, as the pipe is moved in the wellbore, mud actually passes the pipe wall, and a similar effect to pumping the mud is created. So basically, as you're running the pipe in here, this is a surge. You're running the pipe in, you're surging the formation. The reason you're surging the formation is that as this volume of steel goes into the wellbore, mud is displaced up the wellbore to come out the top. And the rate of you running it in will determine the rate of flow upwards of that mud. But there's also the fact that the mud's tending to cling to the stationary annular wall out here and to the pipe wall, which is running down. So you've got this velocity profile created. The mud's flowing up this way, but it's also being pulled down with the pipe as well. So you've got your annular pressure drop, which is the frictional pressure drop acting down because the mud's going up. And you've also got this kind of inertial effect due to the pipe pulling mud down with it. And you end up with an increase in your pressure at the as measured at the bottom of the hole. The opposite's true when you're swabbing. Basically, you're pulling out of the hole, the steel's being removed, so mud has to go into the wellbore, or basically come down the wellbore. It's not just coming in at the top to replace it. As you pull this volume out, the mud's actually flowing in underneath the pipe, trying to replace it. So the mud's actually coming down here. It's got a downward velocity. Therefore, basically the frictional pressure drop's now acting up the way. Mud's coming down the way, but you're also pulling, in effect, mud's clinging to the pipe, and it's also clinging to the borehole wall, so you're effectively sucking some mud up to a certain extent. You could think of it as being sucked up. A bit similar to a syringe, although not really. A lot of the time, people suggest it's very like a syringe being moved in and out of a plunger. out of the syringe barrel, but it's not quite like that because we've actually got quite a large annulus here. You know, the ratio of annulus to pipe is about 0.59, as I said before, so there's quite a large volume here, so it's not quite like a syringe, but you can think of it. As you pull the barrel of a syringe out, it's sucking stuff in through the needle end, and the same when you're running it back in, it's basically ejecting fluid. You're creating a pressure, a downward pressure. It's similar to that, but this explains how it works in a borehole. So as the pipe moves down, the mud appears to be flowing up the annulus past it, and therefore an increase in pressure at the bottom of the hole can be noted, and the converse is true as the pipe is pulled. So the same equations are used to work out the annular pressure losses as you would use when pumping mud. So the relative annular fluid velocity, which is basically the velocity of the mud in this case, is given, or VAE as it was in that previous equation, is given by this equation. This is just to summarize here. We've got K and your diameter expression times the velocity of the pipe. The velocity of the pipe is basically the average speed in feet per minute, or it's the run speed from, take the run speed from INSITE, basically. And the annular pressure loss can then be expressed as an equivalent mud weight as follows. I mean, it's basically your hydrostatic pressure equation. The equivalent mud weight due to surge is the density plus the pressure drop in the annulus using this mud velocity, as opposed to, I mean, substituting the equivalent annular velocity, where K is 0.45 approximately, divided by 0.052 and divided by the TVD. And in the case of a swab, we've got your swab equivalent mud weight gives you your mud density minus the pressure in the pressure drop in the annulus again, divided by 0.052 and TVD. So you're subtracting your annular pressure drop for a swab, and you're adding it for a surge. And that basically explains roughly what our software does. I mean, basically, it's a little bit more complex than that. It does a little bit more than that within our software, but that's the principle behind it. Now, why is it important? Well, more than 75% of all well control incidents are trip related. And the reason for that is that we're swabbing stuff in. As we pick up, people are very keen to get out of the hole as quickly as possible, possibly because they want to get back in and start drilling before some of the reactive formations and so on start reacting with the mud. That need for speed, the need to pull out of the well, can quite often cause people to pick up far too fast, and then they swab in some gas. That's a well control incident. And in fact, I think one bit of literature said 75% of all blowouts, and I've said here just 75% of all well control incidents. That's a fairly accurate figure. They're trip related or swab related. Two places where you can really get, well, anytime you pick the pipe up, you can swab something into the wellbore. So it's very useful to be able to calculate what the swab pressure is likely to be. Therefore, that's why we have the modeling software. More useful still would actually be being able to measure the surge or the swab pressure. So that's where our PWD tool comes in handy yet again. If I have a look at, this is just a stripped down log just to show the important parameters on here. We've got bit depth showing that we're running into the wellbore. The bit depth's increasing as we come down in this column here. We've got run speed here showing as each stand is run in, we've got a positive run speed, then back to zero when it's in slips. A little bit of a negative run speed just as they pick up to go into slips. So that's what's going on. We've got running into the wellbore, picking up to go in slips, running into the wellbore, pick up to go in slips, we're in slips again, run in. All the way down here, we've got a variety of different run speeds. But in general, we're around about, up here we've got about 60 meters per minute. Up at this level, and from a static mud weight of around about 1.625, 1.63, we're actually increasing the equivalent, that's 1.63 SG, or grams per cubic centimeter approximately. But 1.63 SG is the static mud weight. And when we're running in at 60 meters per minute here with the pipe that we're running into the wellbore, obviously the diameter comes into that equation I was showing you earlier, the diameter of the wellbore and the diameter of the pipe. Running in at the 60 meters per minute, increasing the effective mud weight at the bottom of the wellbore, or at the, in this case, at the around the BHA, where your PWD tool is. It's increasing it by 0.1 SG, which is a significant increase. It's huge. So firing it in quite fast in a narrow annulus, you get some pretty big surge pressures. And again, picking up here, we've got quite a big swab pressure. It's gone down to 1.57 SG, which is a 0.06 SG decrease. So we've got some pretty big surges and some pretty big swabs can be seen to occur down the hole. So having a PWD tool in there and knowing the run speed, we now know what the pressure, what the surge and swab pressures are likely to be using the mud as it stands in the wellbore, and we can compare our model to that and refine our model. You know, if we know that what we're modeling is quite different from this, we know the model's not much good, we can maybe just refine something in there, recheck the rheology and recheck the density of the fluid and so on. Make sure the geometry is all in there correctly, and hopefully come up with something that was quite close to reality. The model won't always be perfect, but if we can confirm our modeling software with the PWD measurements, then we can model for future trips and tell them how fast they can pull, how fast they can run in, and so on, without fracturing the formation, you know, exceeding the fracture gradient with some of these swabs, such surges, and without inducing a kick by swabbing too greatly, so you become below the pore pressure, allowing some gas or some oil or whatever to come into the wellbore. Interestingly enough, when you're on a floating rig, you can sometimes, well, quite often you will see a surge and swab being induced due to rig heave. I mean, here we're drilling away and then the weather gets up a little bit. We start seeing that the pipes moving up and down. This is while we're just about to finish drilling and we're about to start pulling out of the wellbore. We're actually seeing a run speed up and down. And the run speed going up and down is actually due to the rig moving up and down. It's floating on the surface of the sea, and it should be compensated due to the compensator on the top of the derrick. But in high seas, sometimes you'll find that bit's coming on and off bottom, or the pipe's stretching significantly as well. So you're getting basically a surge and swab down the hole. And our modeling software, if it's starting to see a run speed here, the INSITE will actually model a surge and swab effect in the hydraulics, real-time hydraulics, and it will have a calculation that does something similar to this. And we can confirm that it's correct by actually seeing the recorded PWD data. Here we've got real-time data while still circulating. That's these red dots here. So you're seeing from something fairly constant to something that's got a heck of a lot of scatter just because the weather's got up. And again, when the pumps are off, the ECD has now become an effective static density because we're not circulating anymore, so it's dropped down, but we've still got that surge swab effect. Again, here we're talking, if this is 1.55, this is 1.6, we're looking about 0.02, 0.03 range there on average, just due to rig heave, which is quite a lot, really. Now, we can actually use our PWD measurements to, and our surge swab modeling to actually change practices on the rig. I mean, basically, this is a fairly old log, but it's still a pretty good one. As we're reaming down into the wellbore, if we'll have a look at this column here, we've got the bit depth, we're making connections as we come down into the wellbore. We've got run speed on here. We've got rotation as we run down, and then pretty much flow in on here as well, so we can see all the connections that we've made as we run down. We're reaming at 10 meters per minute, pretty much on average, approximately 10 meters per minute, and we're getting surge pressures of 1.74 here, over and above a background of about 1.67, 1.675. We're actually going up as high as 1.74 to nearly 1.75 here. Then down here we've got some reaming at 25 meters per minute, and you can see that the surge pressure is actually going up to 1.81 SG, whereas we had 1.74 here. So 1.74 is reasonably significant, but we could possibly live with that. But then the increase in run speed at the crew change, basically, a different drillers come on tower. At the crew change, run speeds increase significantly, and you can see that the surge pressure has also increased significantly because he's running in faster, trying to catch up on the guy on the previous shift, basically. And it's bad practice, that. So basically the ADT engineer says, look, you're going to fracture the formation if you carry on like this. And then he can basically you can model this. You can also back it up with measurements. If there's detection during this while they're pumping, you can back it up with some measurements, hopefully. Certainly back it up with measurements post-run. But then you can change their drilling practices, or their reaming practices. Basically ream in at a nice steady rate, none of this high acceleration just as you're coming out of slips. Rotating and running in fast is a bad practice, because rotation increases your ECD, as we know, and running in fast is also increasing the surge pressure. So high RPM and high run speed going downwards will give you high surge pressures. So just going in smoothly, again, the connections are still pretty steady. We're managing to go down there without necessarily increasing too high. We're not going to go over the fracture gradient. And we've got a nice smooth surge and swab with just by telling to go down a little bit slower. Often it doesn't have to. The overall speed of running in doesn't have to be slowed. They just need to stop this kind of real fast dropping the pipe just at the first and then going into slow. But there's the acceleration, that acceleration at the start, which can give you a large spike just at the start as they start running down. Then it tends to settle out again. So that could be two things. It could be just the fact that it could be your inertial effects, which includes an acceleration of the pipe. It could also be breaking of the gels. If the mud's been static long enough to gel up, then you've got a breaking of the gels and your inertial effects during that initial acceleration. And also just running too fast will give you your effects due to the Burckhardt clinging constant and so on, the actual velocity of the fluid itself, causing an annular pressure drop. Now the following page shows the results of an INSITE surge swab calculation. There's a part of this course that actually shows you how to set up the geometry and go through the calculation. The next page just shows you the results. I wanted to show you this because it's actually recommended that you compare these with PWD observed values before making recommendations. If you get a chance to actually look at the PWD data for surge and swab at different run speeds, you can get this from connections or you can get it from trips. Then compare that with what the surge swab calculation is calculating, and when you're sure that it's quite close, then you can start making recommendations based on your calculation. But and if you can help it, try not to just go with the calculation, because any errors in your geometry or any errors in your rheology or your mud weights that you've put in there will transfer into the result, obviously. So compare reality with the model, and when you know the model's close, use it. Okay, this is the sort of thing that you can actually, the sort of results you'll get actually on the PC screen when you perform this calculation. And here I've just put in start depth and an end depth and quite a large iteration distance just to make the calculation much quicker. But you've got your depth here and you've got your run speed. I've put basically 5 different run speeds in. I've varied the run speed between 100 and 200 feet per minute, and I've done it at 25 foot per minute iteration intervals. So doing it at different bit depths, and you're also doing it at different run speeds, and it's giving you the equivalent density at the bottom of the hole, which is your hydrostatic plus the calculated annular pressure drop added onto that as well. So it's showing that with, I think it was 16 pound per gallon mud here, we're going up to, at 200 feet per minute, down near the bottom of the hole, we're getting approximately 16.41 pound per gallon equivalent mud weight. So once all the pipe's in there, and you're running at 200 feet per minute, that would be basically approximately a stand per 30 seconds, which isn't too unreasonable. A lot of people do run at that speed or faster sometimes. But when you're down near the bottom of the hole and you've got all that pipe there, you've got mud flowing past all that entire annular section, it's quite significant down near the bottom of the hole. You've got 0.4 pound per gallon. On an HPHT well, that could be, the fracture gradient could be about here somewhere, and you running at you're running at one of these speeds could just pop you over that fracture gradient and give you total losses in some cases. So this is the sort of thing you can get from INSITE, and you can also print it out on a sheet of paper as well as a report with a similar 2 sheets of paper it comes out as. One's a tabular sheet like this with a bit more information, and one's a graphical sheet with the same input information on it as well. Right, although I've just mentioned the constraining factors as being the fracture gradient maybe as your upper constraining factor for surge pressure and your pore pressure for swab pressure, sometimes using fracture gradient and pore pressure will give you the ability to basically just run the pipe in as fast as you like, because you're not going to you're not going to swab something in from normal pore pressure in general, and you're not going to fracture rock that's very, very strong. So sometimes the calculation will just say you can run in as fast as you like, especially in things like 17.5-inch hole and so on. So instead of using fracture gradient and pore pressure as my limiting factors, what I tend to do is actually look back at the PWD data when we're drilling and as we're picking up before a connection, running down after a connection, maybe looking at if there's gel spikes or something on a PWD, just seeing what the maximum and minimum pressures were that we managed to withstand while we were drilling, and use the maximum pressure while drilling and the minimum swab pressure while drilling as my limits for tripping. And that gives you a narrower window, but it keeps you within a known, already tested window, rather than using the fracture gradient and pore pressure, which you may end up telling someone they can run a heck of a lot faster than you actually would really be wanting them to do, based on a model with fracture gradient and pore pressure as your limits. So you're now able to describe surge and swab. You're also able to list the primary influences on surge and swab. You should be able to describe the constraints within which surge and swab pressures must be maintained. And you're now also able to understand what's required to effectively monitor surge and swab, monitor and model surge and swab.